through the scoping. I've got a little different example than the one you guys went over in class. Actually, I'm not going to do it in there. We'll do it over here. My pretty artwork. Does anybody want to step through the static example, or just jump to the dynamic example?
I think the static.
You want to go ahead and see the static too? Okay. So, okay. So, if we start this program from, well, you started up here, you see there's a global definition for I. And really the easiest way to do this is kind of just write it as you go. So right now I is equal to nothing, whatever the operating, depending on the operating system, what it initializes it to, but then we start in this first part of main and it sets I equal to 5. And then we, oops, I know there's supposed to be a G. Hold on. Yeah. All right. So we'll set it to 5, and it comes in and hits the I equals I plus 1, makes it 6. So we have, it prints out at the first G over here, prints out G is 6. With a space. And then it falls back out and it comes to this call. That's all right. So we go to F, and then we have a new I. So if we were kind of looking at it, well, basically you just keep track of it. You keep track of it right here, I guess, would be one way to do it. So I equals 3, so we can see that the I is there. And then when we come into here with static scoping, we have a new I with I equals 2, and then we call G. So with G, this I up here, which was currently equal to 6, which one's used? Yeah, the global is used from up here. And so when we get to this part, we hit I plus 1 again, and it's now 7. And then that's what we print. And it falls out, so we were right here. And then we fall into this G. And now I is going to be G falls out, we fall out of the F, hit the return, and we're done. So that's the output expected with static scoping. Just like whenever you write your C program, it works the same way. The global is basically going to override when there's no other variable defined. However, with dynamic scoping, this whole thing changes. So we basically when we get the I here, we'll go ahead and create just a mini table with I, and I has no value at this point until it hits, we start main, and we give it a 5. And then when we come up here in F, we actually create a whole new instance of I. And we set that equal to 3. And then we come into the block here and we actually create a whole another instance of I with it equal to 2. And then we call G. So now when we do I equals I plus 1, which I up here, which of the 3 does it look at when we're doing dynamic scoping?
I equals 2.
Yes, exactly. So it looks at the stack basically and picks the most recent one. And so in this case, it would increment that guy. Oops. Why'd nobody correct me when I made a mistake? Let's go all the way back. We're supposed to go to G first. So we start out with I equals 5. Then we go to G, and we increase this I, because this is the only one when we come here, and that's what we actually print out is G of 6, just like the last problem. And then we call F, and we go ahead and we add this new I with a 3 value, and then we do it again when we come into this next block. We do I of 2, and then we call G, and then as you said, we increase this one, and then print it. So we end up with G of 3. We come back, we return from G and call G again. But since when we fall out of this block right here, we lose this variable, we fall outside of its area, and we're actually in this one. So when we call G, it increments that I. So we end up with a G of 4 printing out, and then it falls out again of F, and so we lose that declaration, and then it returns out, and this is, with dynamic scoping, those are the values that we end up printing. Does that kind of make sense to everybody?
This is the kind of thing we're going to see for the next test?
Mm-hmm.
And you erase everything after the whole thing?
Say that again?
Like what you did for the last 2 I's,
yeah.
You're going to have to show that those 2 are...
It's good to show it, just so in case you make like a copying mistake or you forget to add or something, so they can kind of see the process you were going through.
But they only care about the output then?
Yeah, I mean the output's what you'll be, if the output's correct, then you're good. But we're not computers, so showing your work real quick doesn't necessarily hurt. I think what I did on the exam was I kind of did it like you saw. I just put values out to the right of the definitions next to the I's on static scoping, and then for dynamic scoping, I just built the tables real quick and marked through them as they were gone, as we didn't meet, as they got popped off. Questions? So, you guys have at least talked about it in class. What does, when you're talking about assignment semantics, what does this actually, what does this mean, or what's a way of saying what this means?
The value of my part is the same as your part.
Close. That's good. I think the way that kind of specifically says it is take the value associated with your variable, your var, and copy it into the location associated with my var. So which one of these No, I'm not going to do that. But for precise definition, it does kind of depend on the programming language. And when you're defining a language, there are 4 different concepts that you kind of look at when looking at just what is a variable and how do we use it. You have the name, which is basically just your declaration of it or what you call the variable. Then you bind that name to an address. Oops, I got it backwards. So you have a location that can hold it, and then between the variable name and the location, just kind of abstractly, you have this binding between them so that the variable is linked to an address, and the address is what really the computer cares about. The name of the variable is more for us to be able to follow it through code and understand what's going on. And then finally, you have a value associated with it. So we use the circle and box diagram. Oops. Did not mean to copy that. So we use our box and circle diagrams. I'm going to get the order wrong there. And you take each of those concepts, the name is put there, that represents, the line represents the binding. The location is there or there, really both. You'll see it kind of used both ways in slides and whatnot. So the box itself is just kind of a physical representation of an address, where in the other values, the ampersand X is an address of operator, you guys have probably seen before, and then, or just the actual location of memory, wherever it's located. And then last, the value goes inside the circle, whatever the value is for that variable. Okay, so using this with code, we have an integer, the integer X is assigned, and then with the value 5, what does this mean? What are the semantics of X equals 5? In the kind of in the language that we just used. Yes, exactly. Looking at the box, we're going to copy 5 into the value location of the location associated with X, and this is the association. This is the little bar, the binding between them. So 5 magically goes into there. 5 doesn't have an actual address associated with it, right? So what kind of value is it? Is it an L value or is it an R value? Yeah, it's an R value. It's just, it doesn't have an address associated with it, kind of the definition. L values have an address associated with them, and R values are just values. So we end up with the 5 in the box. All right, now here's another example. We have X and Y. We set X equal to 1, so what does this say it again, just for fun? What are the semantics of X equals 1? Yeah. Copy the value of 1 into the location associated with X. Now, what are the semantics of X equals Y? Yeah. Copy the value and the location associated with Y. I'm going to cheat and read it. To the location associated with X. So you take the value, in this case 1, and this value is in the location associated with Y, and we're going to copy it into the location associated with X. And it just magically goes there. And there's no link between these two. There's nothing. It's just taking that value from one and making a duplicate of it in the other. Whereas if we have pointers or anything else, there could be an actual link between them, and when you change one, that can impact another. So typically you have L value equals R value. I imagine you guys spent a little bit of time talking about how you can't have R value equals R value. Did you guys do that in class? Get that far? Yeah? Maybe? Probably. So as we said, the L value is an expression that must have a location associated with it to be an L value. So you can have an L value on either side of the equals. You would think you could only have one, but it's this. You think you could only have an L value on the left-hand side, but it can actually appear on either side. So this example is kind of interesting. So it's it's important to point this out. Is this code, is it syntactically valid? Yeah. It'll pass the syntax checks, right? It is valid. It's a valid, syntax for C. But is it semantically valid? Does it have meaning when we start talking about L values and R values? How could you copy something into the location associated with 5? 5 doesn't really have a location, it's just a number, right? You could maybe try to jam it in there somehow and say, oh, well, we mean the address of, address location of 5, but that just doesn't make any sense in how the language has been defined. So what, in the language that we're kind of using, what does this say? What does this semantically mean? Yeah, that works. So you could go one step kind of recursively more and say, copy the value associated with the addition of the location of the value associated with the location of B plus the value of the location associated with C into the location associated with A. But that's a mouthful. But yeah, just copy the value of B plus C. So what is the result of B plus C? Is it an L value or is it an R value? Yeah, it's an R value. That's just how we've defined, semantically how we've defined addition is that when you add two numbers, the result that you get is an R value, right? So A is an L value, B plus C is an R value. All that language that we had, and we copy it into there. Okay. What does the ampersand do? It's an address out operator. So what does it return? Yeah, does it return? So if you give it a variable like ampersand x, it returns the location associated with x. So if we were looking at the box, it returns that box value. That's why I had ampersand x and then the address kind of there together, because they both kind of mean the same thing. Is that value, is that an R value or is that an L value that comes out of the ampersand? Both. Both answers. One of them's right. Why do you think it might be an L value?
Because when you say x equals a value, you're storing that value into that box.
Right.
And therefore you're giving out the percentage. X, you're asking specifically for the address, the location of x. Right. Location associated with x.
So if you do, so what we're talking about is doing that, right? What is this output, right? So if we did that's going to print out. Let's see. That's going to print out something like my. Of course, it's going to auto-capitalize, but you guys get it. And it's going to look something like. Something like that. So what does that look? I mean, it looks like just a number that it printed out, right? The result of it is just a number. It's not giving you. It's a meaningful number. The number has meaning, but it's just a number. Just like when we add two results. So the ampersand is just a unary operator. It's kind of like a math operator. And what it returns back is just a value. Just like when you have A plus B, what it returns back is just a value. So there's no location associated with that value. So if we looked at, when it prints out the 8040222, that does have meaning, but it's just a number at this point when it returns it back. So it's actually an R value in this case. The number, it's just a number. It doesn't have, once you place it somewhere or assign it to something, then that variable that you assigned it to has meaning. But the address of operator just returns just a raw number when it's called. So going back. Okay. Yeah, it's a unary operator. Oh, it can only be applied to an L value, so it is the address of operator, right? So it can't work on just a number 5 because the number 5 doesn't have, it's an R value. It doesn't have a value associated, a location associated with it. So it can only find the address of things that have a location associated with it. And then the result is an R value of type T, where T is the type that, so if it's ampersand X, and X is an int, then it is an R value of type of the type needed to point to that value. Sounds confusing. What about the dereference operator, so the star operator? It's a unary as well. It works on just a single symbol. But is it an L value? Well, can it work on an R value? So up above, the address of operator can only be applied to an L value. Can the star operator only be applied to an L value, or could it be applied to an R value as well? Does that make sense? I'm basically saying would this be valid? Well, first, would it be valid syntax? Would it be syntactically? Would that be syntactically valid? Yeah? Unless I made a mistake. Well, okay. No. But now. Yeah. It'd be syntactically valid. What about semantically valid? Like, does this mean anything in the C language? It's a tough question. You can do this. You can get away with this. I don't really recommend it, but you can totally do this. So the star operator, therefore, can work on L values and R values, either one. And then, what is the result?
It finds that location if it's
Yes, exactly. Exactly. If it finds that location, we'll assume the location is writable. It'll find the location. The question will be on modern, operating systems whether that area is marked as writable in the definition for the program. And that 804 on a 32-bit program, it probably is, but which is why I keep using it. But yeah, it would take the value of 5 and copy it into the location associated with 804.0444, and then you'd have a 5 there. And so if you made that statement and then did a print of %d like this, it would, and you ran that, it would print out, well, it wouldn't need the F.